All right, thanks, Nair. So welcome everyone to the third instance of the Quantum BC seminar series. Today we have Prashant Nair, who is an assistant professor at UBC. His primary research interests are computer architecture, quantum systems, AI ML systems, memory systems, reliability, and security. And here at UBC, he leads the Systems and Architectures Lab, or the STAR Lab. So before joining UBC, Prashant was investigating practical data compression for IBM systems at TJ Watson Research Center in New York. And he also has worked on error correcting codes and rowhammer mitigation in DRAM-based memory systems that have been incorporated into commercial systems. So today he'll be talking to us about variational quantum algorithms. So I'll hand it over to Prashant.
Okay, thank you, Olivia. As most of you have already heard, I'm mostly a systems architecture person. And one of my graduate students is working on quantum computing as well. This particular stream of research focuses on variational quantum algorithms, and we are trying to find out ways in which we can optimize this class of algorithm. In this talk, we'll mostly focus on the QAOA algorithm and mostly look at this problem from a more software level and a systems level, and try to figure out how to sort of optimize this problem on a real quantum computer, on a NISQ machine. So what are variational quantum algorithms? These types of algorithms are algorithms that combine classical and quantum computing. So they are sort of hybrid algorithms. They have an optimization loop. And this slide shows that optimization loop, right? Wherein you have a quantum circuit. It sort of gives you an output. You pass that that encodes the optimization problem, and then you sort of pass this to the classical optimizer that is run on a classical computer that computes an objective value, and then based on that value, you sort of pass that back to the quantum circuit. They update the parameters, and sort of you have this loop. Compared to other algorithms, these types of VQAs are more versatile, and they are more noise resilient. They are sort of more amenable to modern day NISQ machines. NISQ as in the noisy intermediate computing machines right now. Furthermore, the fact that they are hybrid enables them to tolerate the limitations that the near-term quantum computing hardware have, right? And we'll sort of discuss how this is done in a little bit more detail in the next few slides. And that's why these types of algorithms are more practical and promising in the sort of the near term. Okay. So one of the case studies, or sort of the algorithm we focus on in the QAOA is the QAOA algorithm. And QAOA is very powerful, right? It has sort of shown to help solve complex optimization problems. One particular problem that it solves very well, or it should solve very well, is the max cut problem, right? Wherein you sort of, or a travel displacement problem, right? Now, how you sort of create, you sort of encode this problem in a quantum circuit is that you sort of formulate the problem, you create a suitable objective function, then you prepare an initial circuit that you select with certain parameters. Then you sort of perform a quantum evaluation process to compute the expected values on this circuit. And then you pass the outcome of this quantum circuit back to the classical optimizer. Most of the classical optimizers use some sort of gradient descent, like an anagrad gradient descent or some sort of gradient descent. And they sort of adjust these parameters that you've passed to the quantum circuit. You also sort of do a convergence check on the classical side. Typically, this is a stopping criteria as to when to sort of stop optimizing. And eventually you extract the solution. So there is this loop, right? And a lot of sort of overheads in terms of performance go into the classical part of this loop. And a lot of the noise related problems exist in the quantum part of the NISQ machine. So ideally, what you really want is that you want a way to sort of maybe take the QAOA problem, maybe make it a smaller problem, right? Rather than a larger, say, graph, you make it a smaller graph. You execute the smaller graph to figure out parameters. And then, because you're using a smaller graph, you probably run a low number of iterations on the classical side. And you also maybe don't have to use a lot more qubits on the quantum side, right? So this is the high level sort of the motivation towards some of the high level motivation that we've taken to sort of solve this problem. And if you notice, the only thing that's sort of executed on the quantum machine is the quantum evaluation, right? Wherein you sort of figure out the expected values. All the other steps are run on the classical machine. Okay. Now, to sort of better understand the challenges associated with the parameter searching process in QA. So because QAOA, what it tries to do is that it tries to select the beta and gamma parameters, and we'll discuss beta and gamma in a little while. But in this sort of graph, you see that the y-axis here is the beta, the x-axis is the gamma, and this is like an energy landscape, right? In this context of QAOA, the energy landscape is a visual representation of the objective value. So here the objective values in dark yellow, the patch in dark yellow have higher objective values, and the ones in dark red have lower objective values, right? And what you sort of want to do in this optimization loop is to sort of somehow arrive on values of beta and gamma that correspond to the yellow regions, right? The highest objective value regions. And this sort of landscape provides an insight into the distribution of the objective values associated with different combinations of parameters. Now, to find the optimal solution in a typical optimization run, the algorithm would start from any sort of random initial value, right? And then sort of navigate its way into the higher energy state, right? Now, this energy landscape is very important, and it sort of plays a critical role in identifying the optimal solutions for QAOA, okay? And you will sort of figure out that how you sort of maybe have understand this landscape and design equivalent landscapes can also help you solve QAOA more efficiently. So what are the key challenges here, right? There are obviously several critical challenges. For instance, there is the problem of expressiveness, right? The initial circuit, the answers, circuits for the solution space representation may not be efficient, right? And these circuits may not capture the problem's essential features while requiring minimum quantum resources. So it's possible that you have to sort of dedicate a larger, a deeper circuit, for instance, to solve the problem, right? And that could, in today's age, cause loss of fidelity in the outcomes, right? The optimization process on the classical side is not robust to noise, right? So if the quantum circuit gives you a solution that's noisy, right, the outcomes are probably incorrect, then the optimization loop, right, the classical side might actually misinterpret this outcome, right? And there's no easy way to solve this. You have to either have a more robust quantum computer, right, or design a better optimization algorithm. Another problem with this in this area is the problem of barren plateaus, right? There could be regions in this energy landscape where the gradients may not change as much. So there are vanishing gradients in this parameter space. And when that happens, you're sort of stuck in this plateau. You don't actually come out of this plateau. And this could sort of hinder optimizations, right? And lastly, more importantly, sort of adapting QAOAs or VQAs to near-term quantum devices is quite difficult, right? Because near-term devices have limited qubits. I mean, I know that several industry players have sort of promised to give us a few hundreds to 1,000 qubits, but even that may not be enough, right? When you have to run maybe very large graphs. We also have sparse connectivities, right? As you sort of increase qubits, at least in some of the industry quantum computers, you'll notice that the connectivity between qubits tend to be more sparser, and the coherence times are also not increasing at the rate at which we want. Right? So you sort of want a way that sort of adapts the algorithm with the current hardware limitations and make it sort of palatable for the current hardware. So let's look at the some of the noise-induced challenges, right? In QAOA, clearly, when you have a quantum circuit, there are gate and measurement errors. There are coherence time concerns. This sort of causes qubits to lose their quantum state, and this sort of causes results in suboptimal results. This noise can also distort the optimization landscapes, like I just mentioned, and you could introduce more local minima and maxima and trap the optimization problem, right? So rather than go to the actual ideal outcome, you can actually be trapped into noisy because of noise. The landscape could have additional sort of plateaus and troughs. The gradient estimation, right, may be compromised with noise. This sort of makes it challenging to identify the correct direction for the parameter updates based on the gradient-based optimization methods. Of course, all of this causes robustness issues. When you have larger algorithms in size and complexity, and the size of the circuits increase, you can see fidelity issues, right? And this is obviously a very big problem. And these challenges are going to become more problematic for larger quantum algorithms due to increasing influence of noise. Okay. So these were sort of the high-level motivations as to why we sort of approach the problem as we were to approach it, like we'll just see right now. And we used QAOA because we thought that this is sort of a promising algorithm with real-world implications. So let's look at how the noisy landscape appears to be distorted, right? So on the left side here, you have the landscape with beta and gamma values. And this is the ideal landscape, right? On a 13 qubit circuit. And when you actually execute this on the IBM machine, you get the landscape on the right, right? You can see that there's some noise-induced distortions, right? And these distortions sort of make it challenging to achieve the desired result when optimizing for an objective function, right? So one of the ways we can sort of view this problem is that when the problem size becomes larger, the problem would require a larger number of qubits and probably deeper circuits. So what we really want is a way to solve the problem using smaller graphs, thereby making the problem smaller in size, and be able to transfer the parameters that you get from the smaller graphs into larger graphs, right? So if you have a larger graph, you sort of figure out parameters using a smaller graph, and thereby sort of use those parameters and transfer this to a larger graph, right? This is sort of the parameter transferability of QAOA, right? Once we've obtained the optimal parameters, we can directly transfer them, right? And because we've sort of, maybe in some cases, we can keep a database of parameters, and we have trained those parameters on other instances beforehand, we'll be significantly able to improve the fidelity or the efficiency of the optimization parameter search process, right? So typically in QAOA, you sort of represent the problem as a graph with edges and nodes, right? The gates represent edges. Okay, so these edges are here. The green edge represents, so the green sort of, the green circle here, the gates here represents this edge, and the blue circle here, the gates here represent this edge. And based on the input graph, you sort of see a different circuit here, right? And the graph edge corresponds to a specific set of gates, and here we have blue and green, and then you sort of get sort of an output distribution value that you feed back to the classical optimizer. Now, to just see how the expectation value is computed, and this is important because we'll use this insight into how we optimize the problem, right? We see an example here with 5 nodes and 4 edges, right? So 0, 1, 2, 3, 4, 5 nodes, and these 4 edges, right? Now, to calculate the expected value f of p corresponding to the beta and gamma values indexed from 1 to p, where p represents the total number of QAOA layers. So you have several layers of these computations that you sort of have to do to be more precise. We examine the equation, right? Even though this equation appears to be lengthy and complex, majority of the terms are just repeated, right? And they have interweaving layers of the same operators, right? And the key takeaway here is that f of p, right, is a summation over the terms j and k, right, where each j and k term corresponds to one edge in the graph. Okay, and by rewriting the equation accordingly, we can sort of have an equivalent expectation value that equals to the subterms c, j, and k, right, each of which represent a single edge, right? So if you take a 4-node graph, right, a 4-edge graph, sorry, we can now write down the terms in the summation in this way. Now, if you want to sort of look at this a little bit more clearly, let's look at a simplified scenario, right? Wherein we fix the number of QAOA layers to just 1. That's sort of simpler. And each sub-expectation term evaluates to a subgraph then, right? So here, this term becomes this subgraph, right? This term becomes this subgraph. This term becomes this subgraph. And this term becomes this subgraph. So you know what I did here? I took the graph. I broke the graph down into subgraphs. Now, because these are 4 subgraphs, and if you notice, some of these subgraphs have fewer nodes, right? You sort of decompose this problem, right? Now, the second thing we observed is that given a graph, right? Let's say you have 2 of these random graphs. If they can be all decomposed to the same subgraphs or nearly same subgraphs, they tend to have similar values, right? In terms of f of p, you can sort of get the same beta and gamma values, right? So this is the core concept behind our proposed methods, right, for addressing noise. So if you have a large graph, form subgraphs, you'll find several subgraphs. Now, if those subgraphs, if the parameters for those subgraphs are pre-computed, let's say we have a database which have pre-computed the values of these subgraphs, we can use the database. Or maybe we have some other techniques that we'll discuss later to use these subgraph values, right? Now, people have proposed similar techniques before, but there were some issues or sort of constraints on those parameter transfer, right? The researchers that have proposed this have looked at parameter transfers that are mutually transferable between subgraphs of the donor graph, right? So what this means is that all subgraphs of the donor graph should have the same optimal QAOA parameters, right? Similarly, right, the graph that accepts these parameters, the QAOA parameter should also be transferable between all its subgraphs. Right? This is sort of their precondition. And optimal QA parameters should also be transferable between every subgraph of the donor and the acceptor. So this is a highly constrained set of prior work, right? Wherein they're telling you, well, you can transfer parameters, but then you have to meet all of these conditions, right? And what typically we can do here is that, let's say we have 3 examples here, right? So the input graph looks like this, let's say number 4, right? Maybe if you know an appropriate donor graph, then we can actually use the parameters of this donor graph for this acceptor graph, right? So 1 to 4, you can sort of transfer parameters, get similar energy. This is, I guess, sort of the average energy number with very similar approximation ratio, right? So once these strict preconditions are met, right, one can successfully transfer parameters from a 6-node graph to a 64-node graph, right? With only, let's say, with a 2% decrease in the approximation ratio, right? Now, clearly, if you were to execute a 64-node graph, you would need to, without transferring parameters, you would have a significantly high computational load on the optimizer, right? You would also have to have 64 qubits in your NISQ machine being used. It's not going to give you any meaningful result, but you could probably execute a 6-node graph fairly easily with lower errors, and it also sort of not place much pressure on the optimizer, right? So, but there are these strict preconditions. Okay. Now we sort of aim to overcome these preconditions, right? And we sort of aim to do it for irregular graphs. So the previous work sort of focused on regular graphs, and we noticed that most graphs in practice in the real world are irregular graphs. So so here I think there are some questions. Oh, okay. So Meng, thanks for answering that. I didn't look at my chat yet. Let's just continue. I think Meng's answered that. Yeah, so we've sort of focused on the irregular graph. We also have some techniques which we call reduced QAOA or Red-QAOA that tries to reduce the circuit size using some other techniques. Okay. So the first work called GRAF sort of translates this problem into more of a database problem, wherein you keep a graph database, a reference that consists of several thousand graphs that have optimal parameters pre-computed. And you sort of reference into the database for these optimal parameters. And once this database gives you these optimal parameters, you sort of feed that in, right, into the gradient descent process. So rather than having search through the energy landscape randomly, the graph database can sort of give you a more directed search. Okay. And why does this work? This works because we generalize sort of this idea considering a different metric, right? Rather than looking at exact matching of subgraphs that previous work did, right? We sort of looked at the edge count difference versus the max cut difference, right? And since the diameter of subgraphs is fixed and equal to the number of layers, right? The key difference between subgraphs lies in the total number of edges in the subgraph. Right? And we demonstrate this by plotting I think 457-ish graphs between 2 to 9 nodes and 2 to 21 edges, right? And you can see there's a clear correlation between the graph's max cut value and the number of edges in the graph. And the smaller the difference, right? In the number of edges between two graphs, the closer is the max cut value. So based on this insight, what we do is that we sort of use the edge count distribution as a metric to match input graphs with pre-optimized graphs in the database. The database is preloaded with the optimized graphs. And what we do is that we take the input graph, we break them into subgraphs, we sort of get the edge count frequency distribution. We use this to index into the database. It has several fields, the mean, the standard deviation, the number of nodes, edges. And given these terms, we get the value of beta and gamma. And these are sort of features, right? And we sort of use these features from the database to sort of get the values of beta and gamma. Now, Graph provides two options. You can either sort of use these values beta and gamma directly, right? We call that the direct transfer. Or we can have a warm start, wherein the beta and gamma values may be imprecise or slightly imprecise. And we sort of land close to the optimization point in the energy landscape. And we start the gradient descent from that point, right? And we handle these two approaches differently. For direct transfer, we sort of use the median parameters of 10 instances. In contrast, for warm start, the sets of parameters serve as initial points, and then we sort of start from those points to further improve results. And the figure of merit in this work is the approximation ratio. So what the approximation ratio tells you is how far or how near your outcome is compared to the ideal outcome, right? So that's sort of the figure of merit. We do have several benchmark graphs. I think we use this, the graph dataset from the QAOA kit, which contains the optimized parameters for all unique graphs for up to 9 nodes for the graph database. And essentially, in this figure, we notice that as we vary the number of nodes, we sort of plot the reduction in approximation ratio for 7, 8, and 9 node graphs. Each graph is also evaluated with 1, 2, and 3 QAOA layers. The donor graphs used in this case have 2 fewer nodes. The figure demonstrates that graph, our ideal, exhibits impressive performance, even without employing gradient descent. So these are direct transfers, right? Because we notice that we are getting very close to ideal approximation ratios. And as we move to larger graphs, graph, our ideal, actually produces more improved results, right? With the final approximation ratio for a 9-node graph to be less than 1.5 percentage points as compared to the optimal value. So what these findings underscore is the effectiveness of this direct parameter transfer in the framework. So this figure here looks at the warm start technique, where the number of optimization runs on the x-axis is varied, and the success rate is shown on the y-axis. So in the baseline, right, you can ignore the top 3 lines here. The baseline would have to start at random points and do a gradient descent from those random points in your energy landscape. Whereas in the warm start, the graph database provides you with some preset points, which are probably maybe close to ideal. And from there, you can sort of quickly converge on the final value, right, the optimal value. So in almost all instances, you will notice that the lines on the top, right, which are lines from graph, always sort of converge or reach the success rate of 100. I think success rate is derived from approximation ratio. Meng can probably correct me if I'm wrong. As compared to the baseline optimization runs. One other sort of key thing that you notice here is that for larger number of layers, right? Let's say p equal to 3, the baseline maybe requires 50 or even more runs, right? In most cases. But it still doesn't reach a success rate of greater than 80 or 90%. Whereas if you were to sort of start from somewhat optimal values from the database, you can actually get close to ideal result very quickly. Very few optimizations runs are required, right? So this sort of is also an efficient usage of the quantum resource and the classical computer here. So on that note, we can look at how it saves compute. If you look at the average circuit execution per optimization run on the y-axis and the QAOA layers on the x-axis, not only do we converge to the optimal solution faster, but we also, since the initial points are much closer to the final solution, we only require fewer iterations, right? And you'll notice that there's a computational usage for graph savings for graph and random initialization sort of increases, right? So if you randomly initialize, you sort of require a larger number of compute time, right? It sort of increases as the value of p increases, right? Because when you sort of increase the value of p, that is the number of layers, the parameter search space increases dramatically. And that's why the baseline actually takes much longer. But graph does not, because it sort of starts at close to optimal values. This is sort of an example that we sort of show to represent the effectiveness of our idea, a visual example. So here we have a testing graph. And this testing graph, the blue sort of stars indicate the global maximum. This is where you sort of have to land for values of beta and gamma. And the green points here, right, and here represent the initial points that graph tells you to start from. So because these initial points are so close to the global maximum, right, intuitively speaking, the amount of gradient descent operations that are required to reach the global maximum is not large, right? So this is intuitively why graph works. So the database sort of gives you pointers to sort of reach these points, right? And you sort of start from there. You'll notice that it's not always the case that you'll be close to the blue bar. You also have cases here, like, I don't know if you can see my mouse, that sort of have a point that's farther away, right? But most of these points are closer to the global maximum. That's sort of the high level point here. And there are limitations, right? The dataset preparation is challenging, right? As it requires significant effort and resources to prepare this, generate this optimized set of parameters for all unique graphs. This could be a limiting factor, especially for large complex graphs. Note that we only need to create this database for all the subgraphs, right? Because we are decomposing this problem into subgraphs. Another concern is the scalability, right? Our idea does show promising results for up to 9 nodes, but there is no clear indication that it will sort of scale well for larger graphs. It's possible that the performance of the method may degrade as the graph size increases. And from the traditional computing point of view, it could be that our graph database size actually increases. If that increases, then maybe graph database lookup operation actually consumes more time, thereby sort of introducing more computational overheads. Additionally, as the number of QAOA layers increase or P increases, it becomes harder to transfer parameters between graphs. Empirically, it has been observed that transferring parameters for higher value of P becomes more difficult, right? It's because of the larger sort of search space and then the larger number of subgraphs. So like looking forward, future research sort of that we are sort of looking at would focus on addressing these limitations, right? And we sort of want to make this idea more robust. And we sort of want to focus on sort of these vectors as well in sort of the future work. Okay, so that's the graph idea. Again, these are preliminary numbers. It looks promising. We are in the process of sort of doing more experiments and making sure that we sort of tie all loose ends, especially these limitations, these common concerns. But we thought we would present this here sort of to get feedback. The next problem that we sort of tackle is called the Red-QAOA, right? So we've looked at the graph problem. What graph problem does is that it tries to sort of break down a larger graph into smaller subgraphs, you use a database to look up these parameter values. You get the parameter values, you use them in the search process, in the gradient descent process, or directly use them, and thereby sort of save the computation time and also sort of converge on optimal parameters more efficiently, right? The Red-QAOA sort of idea aims to address challenges associated with the parameter searching process. So right now we haven't addressed the parameter searching process, right? You still have to search the parameters either beforehand and load them onto the database, or you have to do this adagrad gradient descent sort of operation, right? So rather than focusing on subgraphs, what this Red-QAOA does is that it takes a different perspective, right? It tries to take perspective of transferring parameters between entire graphs, right? Now, this is motivated by the fact that the energy landscapes of similar graphs is similar, right? And not just the optimal points. So here the QAOA landscape for a 10-node cycle graph and a 7-node cycle graph are presented, right? And they almost showcase identical energies, right? So if there's a way in which we can sort of reduce the input 10-node cycle graph to a 7-node cycle graph and we can sort of search for parameters using the 7-node cycle graph, right? And to quantify the similarity between these two graphs, we use something called as the mean square error, which computes the average point-wise difference in the energy landscapes. A small mean square error, or MSE, indicates that the overall shape of the energy landscapes between two graphs is almost identical, right? For instance, in this figure, the MSE between the 7-node and the 10-node normalized energy landscapes is 10 to the power minus 5, in the order of 10 to the power minus 5, right? So it's almost similar, right? Now, this idea, Red-QAOA, also has the potential to overcome the limitations of the graph, right? Now, GRAF required you to construct a database, and fine, for a 9-node graph, it's okay. But what happens when you have a 100-node graph, right? You have so many possible subgraphs. While it is computationally possible to generate a database that holds all those subgraphs, it's sort of better if you don't have to do that. What if you can sort of transfer between entire graphs? You don't actually have to create the database, and thereby sort of ensuring scalability. So this is the overview. What we do is that we sort of take the graph G here. We employ simulated annealing. We'll also look at other graph pooling techniques. And in this reduced graph, which is G dash, we do the parameter searching, right? Because the G dash graph eventually can be executed on a smaller quantum processing unit, and also it's a smaller graph, right? You eventually end up with more accurate parameters. Now, using those accurate parameters, you sort of reapply those parameters back into the larger graph G, and you run that on a traditional quantum processor. So this is sort of the high-level overview of our idea. And why use simulated annealing? We use simulated annealing because it's sort of a graph reduction method, right? And it searches for the smallest subgraph in the original graph that satisfies a certain threshold of average node degree. So here, if you look at the average node degree ratio, right, going from, I guess, 0.1 to 1, and the mean square error, right, you'll notice that at an average node degree ratio of 0.1, sorry, 1, the mean square error is almost close to 0, right? So this approach is based on the observation that there is a correlation between the average node degree ratio and the mean square error in the energy landscapes of these graphs, right? As the average node degree ratio approaches 1, the mean square error of the energy landscape is essentially sort of limiting, right? Enabling the idea, Red-QAOA, to efficiently reduce the input graph size while preserving information about the energy landscape, right? And if you have to see this more pictorially, right, this is how it looks like. If this is the reference graph with beta and gamma here, and the blue stars indicate the optimal points, right? As the mean square error varies, right? Here the mean square error is increased by 0.1, and you'll see that the this energy landscape looks very similar to the reference landscape, and also has very similar values of beta and gamma that are optimal, right? So you can sort of understand that if you sort of randomly select 6, here we have 6 10-node graphs, and plot their energy landscapes, and if their energy landscapes are normalized between 0 and 1, right? We observe that as soon as the energy, this is empirically observed, we still have to sort of look at the sort of deep dive into exactly why this is going on, what's going on here. As soon as the MSE sort of exceeds a certain value, let's say 0.2, right, the location of the optimal points sort of diverged, right? But if it's less than that, and if the two graphs are equivalent, right, you get very similar energy landscapes. Okay. So what Red-QAOA does is that it iteratively adjusts the nodes reduction ratio. So it sort of tries to reduce the number of nodes. It tries to find the best subgraph that adheres to this, right? It checks if the subgraph's average node degree ratio meets the threshold, in this case 0.75. That's what we have in our algorithm. And then we adjust the reduction ratio. So we iteratively sort of try to string the graph, right? And if the threshold is not met, we try to find smaller graphs. And if the threshold is met, we try to find smaller graphs. And if the threshold is not met, right, then we sort of decrease the reduction ratio. So we just find larger graphs. Okay? And we terminate this loop once there is no improvement. Okay? And once we find this reduced graph, we use this reduced graph to find optimal parameters. So to sort of study this idea, we used some publicly available graph datasets, namely AIDS, Linux, IMDb, and Random. AIDS contains 700 chemical compound graphs, representing chemical compounds with 2 to 10 node graphs. Linux contains 1,000 function call graphs extracted from the Linux kernel source code with 4 to 10 node graphs. IMDb contains 1,500 movie collaboration networks with from the movie Internet Movie Database. I guess it has up to from 7 to 89 node graphs. And we also include 10 randomly generated graphs with 720 nodes, just to sort of see how it performs. Right? And what we noticed is that when we sort of evaluated Red-QAOA in recovering the ideal landscape for graphs within 7 to 14 nodes and compared it to the baseline methods, in this case, the y-axis is the noisy mean square error and the x-axis is the number of qubits. The noisy landscape obtained, right, using simulation. So here this is simulation. Using Qiskit's 27 qubit fake Toronto backend, Red-QAOA consistently outperformed the baseline method in terms of MSE in the presence of noise. So once you have noise, even if you generate sort of an approximate graph, it's still better because the approximate graph, the approximate landscape represents a smaller graph, right? So even if you have noise, even if the landscape is approximate, if the landscape represents a smaller graph, you sort of always do better in terms of MSE, right? Moreover, we selected 2 specific cases to investigate in more detail, right? A 10 input graph with the largest reduction and 11 input graph with the smallest reduction, right? So these 2 cases. So the best case is a 10 node graph. And you can notice that as compared to the ideal value, the Red-QAOA still gives you the same sort of the optimal numbers of beta and gamma in the same regions, right, of the landscape. Whereas if you have a baseline, which is noisy, right, you see that the blue is sort of all over the place. So it's not able to converge correctly. Whereas Red-QAOA, because it uses a smaller graph, it was sort of able to sort of converge, at least closer to the ideal one. And even in the worst case, right, in the 11 node graph case, we see that QAOA continues to sort of give results close to the baseline. Right? So this sort of indicates that we are the Red-QAOA is robust, right? How effective is it in identifying similar graphs? If you see the reduction ratio in terms of nodes and edges, we notice that you have 20, 30, sometimes even 40% reduction in terms of nodes and edges, right? And even if you sort of look at these different data sets, the mean square error is quite low, which means that this technique is very effective in terms of identifying similar graphs, right? And can it scale to larger graphs? Yeah, I mean, that's what we noticed. When we sort of looked at the IMDb dataset, right, because it had the worst performance, we extract 2 subgraphs from the IMDb datasets for further evaluation. One is the small one and one is the medium one. The small one contains 10 graphs, so graphs with up to 10 nodes, and the medium one contains graphs with 10 to 20 nodes. When we move from small subset to the medium subset of the IMDb graphs, the node reduction ratio increases from 15 to 25%. That's because even when you have a larger graph, when you do simulated annealing, you still converge to a relatively small graph, right? So in terms of reduction, it's sort of a larger reduction. And the edge reduction ratio also raises from 28% to 35%, right? We also sort of notice an overall reduction in the mean square error, right? Now that's because when you have these medium-sized graphs, if you run it on a real machine, good luck with it giving you any meaningful outcome, right? Whereas when we actually use our technique, because we now reduce this graph into a smaller graph, we do get some meaningful outcomes. Right? So this is sort of proven to be an effective solution for even larger graphs. And we sort of did a device execution as well. This is the execution on a real 27 qubit IBM Kolkata machine. This is the ideal landscape. This is the Red-QAOA landscape on this machine. You'll notice that the blue parts of this landscape coincide with the ideal one, whereas this is the baseline system that does not employ Red-QAOA, and you notice that the optimization points are all over the place. So this sort of indicates the strength of Red-QAOA even on real systems. Now, what this helps us to do is that once you have a 27 qubit machine and you don't use 27 qubit, let's say you use 13 qubits, you have 13 qubits that are free. So you can actually improve throughput, right? You can use those 13 qubits to run something else. Although that could cause some interference, but there are techniques out there to do multi-programming. I won't go into those. But once we do that, we sort of improve the throughput of a quantum machine. Already quantum machines are scarce. So something like this is actually very useful because now you can actually reduce the problem size, make it more efficient to run, and also improve the throughput of the quantum machine. Right? So we've improved throughput by 1.8x, sometimes 2x, sometimes 1.4x sometimes. This depends on the size of the graph. IMDb has larger graphs, I think. So that's why it sort of could not improve throughput as much. Now you might say, why use simulated annealing, right? Why not use some other graph pooling methods, right? Now the reason why we use simulated annealing is because, and we sort of compared it with something else. We use something called as additive self-attention, which is one of the graph pooling methods, and set attentional aggregation, SAG, which is another graph pooling method, and top K pooling, right? So these GNN-based pooling methods used fixed reduction ratios and do not dynamically check if the reduced graph approximates to the original graph, right? Whereas the simulated annealing has an adaptive component in our design. I didn't go into it a lot more detail, but I can share an archive version of this paper maybe in some time. And that sort of helps us be more efficient as compared to other pooling techniques. If you notice, the purple line consistently beats the lines for ASA, SAG, and top K, right? So SA is simulated annealing. So simulated annealing is almost always better because it almost always converges on the right or the relatively better set of subgraphs, smaller graph as compared to the other pooling methods. So this sort of highlights the importance of developing specialized graph reduction techniques that are tailored to the needs and the constraints of QAOA. So just to summarize, we present GRAF and Red-QAOA, both of which tries to utilize the parameter transfer property to reduce the graph parameter search overhead associated with QAOA. GRAF creates a database and infers optimal parameters for input graphs from this database, whereas Red-QAOA reduces the size of the input graph to reduce overhead. Although GRAF has higher potential savings, it faces some major limitations at this stage. We are still working on this. Meanwhile, the Red-QAOA is more practical. At least that's what we found. We actually ran this on a real system as well. We just showed that. And we sort of saw that it's more effective and more scalable for QAOA parameter searching. Overall, the Red-QAOA framework presents a promising approach for reducing the impact of noise on QAOA and parameter searching. Thank you. And this was a work that is primarily driven by Meng. I think Meng is on the chat. He's answering questions. So thank you for that. So I should thank him also for doing this work. So thank you, everyone.